Hi guys, welcome to my lecture series on states of matter. Now before we start, I want you to do something really important. I want you to just breathe in and breathe out. Breathe in and breathe out. Great, you're living. So, what we've just done is exchange nitrogen, oxygen and carbon dioxide in their gas phases. Okay, if we look round sunny Swansea, we have a heck of a lot of water in its liquid phase. And if I jump up and down, I sit on rock that's in its solid phase. And if we go deep down, we increase the pressure and temperature, we're going to encounter rock that's passing what's known as its solidus and starting to partially melt and return back to its liquid phase, and the whole cycle for rocks starts again. Okay, so these are all examples of states of matter, and we've used them.
I'm just going to stop myself there, and wow, look at that face. I wish I could move it on just a little bit now. Anyhow, so welcome to the lecture series on states of matter, and we're going to be focusing in the next few lectures on solids. Before I carry on, I just want to marvel at the moment that we've been using a little bit of knowledge on states of matter for about 5,000 years, ever since the first person took a lump of rock, heated it up, smelted the metal out of the rock, poured that molten metal into a mold, and then cooled it quickly and basically shaped it into a tool that would then significantly enhance our development as human beings, or maybe not, but that's a whole other debate which we're not having here. Anyhow, if we hark back to the practical last Monday, you had an opportunity to have a look at some minerals. Some of them would have been quite familiar to you, some of them maybe not. So what is a mineral? A mineral is a naturally occurring, it's homogeneous inorganic solid. I bracket apart from mercury, which is liquid at room temperature, and it has an ordered atomic arrangement and a chemical composition that's fixed within known limits. So if you do an elemental analysis on a mineral, you can pinpoint almost exactly, well, you can pinpoint exactly what that mineral actually is. As I said, some of them would be familiar. So you saw some very regular looking quartz, you saw some hematite, you saw some gypsum, and micas as well. So these have what's known as a crystalline structure. They have regular internal structure built up of small repeatable units. And they're predictable, so you should be able to predict where an atom is going to be in its location, its position, further along that crystalline structure. Okay, so I mentioned quartz, which had that lovely hexagonal structure. I'll come back to that. But it's basically, well, that hexagonal structure, and sometimes amethyst, which is closely related, that's sometimes a trigonal structure as well, that comes from that repeatable kind of unit inside. So that regular structure, it manifests itself in that lovely sort of external crystalline regular structure. And we looked at different properties. So quartz is quite hard, it was vitreous, and then next to that we had some talc, which is really soft, it has the Mohs hardness of 1, and gypsum, which again is soft. And this little picture on the left hand side is actually a scanning electron microscope image of gypsum. It's absolutely tiny, this crystal, but what you can see is this amazing fishtail twinning, which actually occurs due to a crystal defect at a growth boundary. Gypsum is used in gypsum plaster, so it's used in the construction industry. There are also other uses for gypsum. It's an evaporite. It forms when you dry up seawater, so it forms in hypersaline conditions. There's great swathes of it across around the Mediterranean, and in fact during the Mycenaean, the Mediterranean almost completely dried up and sort of got large evaporite deposits, which is sort of commercially viable. Anyhow, that's digressing slightly. We saw mica. Mica is amazing. So those are those little sheets of silicate. So lots of our minerals close to the surface are silicates. The crust is very rich in silicates. The reason is the fact that during the early history of Earth, during the Hadean, we had what was known as differentiation, as the Earth was molten, so the heavy elements sank to the core and the lighter elements were displaced and came to the surface. Mica can be ground up, used in cosmetics. It can be used in its ground up state in plaster. It can be ground up and used in paints to give it a metallic sheen. And what's quite incredible is, you know, those very thin sheets, a single sheet of mica is actually atomically flat. So if you want to do any scanning probe microscopy and you want to gold coat a atomically flat surface, then mica is your mineral. Anyhow, let's go back to thinking about silica and quartz. So this is, any ideas what this image is on the right hand side of the screen? I'm going to give you a very awkward silence, a pause here. Okay, it's actually the remnants of a very old radiolarian. A radiolarian is a little single-cell protozoa which lives at the sea surface, and it builds these incredibly intricate sort of hard parts out of silicon dioxide. So exactly the same as the quartz that's on the beach. The quartz, you saw this nice hexagonal structure. However, this is biogenic quartz. It's pretty much amorphous, and just like the glass you had your pint in, that's also amorphous silica. So you can basically take sand from the beach, heat it up until it's basically liquid, and then reform it into glass. Okay, so amorphous silica doesn't have what we talked about earlier. It doesn't have this repeatable and predictable structure. So it doesn't have what we call this long-range order. So structurally, it's actually kind of akin to a fluid. Now, have you ever heard that myth that glass is actually like a non-Newtonian fluid? It actually flows. So, you know, the idea is a supercooled liquid, and this is why medieval glass is thicker at the bottom than it is at the top. Well, glass is an amorphous solid, okay? It is not a liquid. Basically, a supercooled liquid is one where it's cooled quickly from its liquid state, but doesn't completely solidify when it drops below its melting point. If glass is cooled further down below its glass transition temperature, then it forms this amorphous solid, which glass is. But it's disorganized. Okay, it's amorphous. It doesn't have this regular pattern. It's disorganized, as we know from thinking about entropy. Things like to move from a more disordered high entropy state to a low entropy, more ordered structure. So over time, yes, amorphous glass will actually reorganize its atomic structure to become more regular and more stable in its crystalline structure. But we're talking billions of years, not the hundreds of years we're talking about medieval glass. In fact, if we look at the methods of glass blowing, it was just the fact they were blowing them into cylinders and then shaping them flat. And this is probably why we ended up with this irregular shape. And for some unknown reason, medieval glaziers decided to put them that way up when they installed them. Now, if we look at Egyptian glass, we don't see the same in that. So the whole theory that glass is a non-Newtonian fluid just does not hold water. It depends if you've broken your glass, I guess. Anyhow, in the following lecture series, we're going to be exploring different types of bonding in solids and crystalline structures, and we're going to look at how this gives rise to different physical properties. We're going to look at how unit cells are kind of arranged and their packing arrangements, and we're going to describe the crystal structures that arise from it. We're going to understand what a polymorph is and what an allotrope is. We're going to understand more fully why metals conduct electricity when a potential difference is applied to them, and why superconductors exist and why they behave in the way in which they do. Okay, without much further ado, I'll move on. So I won't dwell too much on this slide at all. We know here on the far right hand side of the screen, this is an idealist picture of a gas. We've got molecules that are moving far apart from each other quite randomly, bumping into each other, colliding at really high entropy. And then lower entropy state, we have our liquid, where molecules can slide past each other, they can say hello, they can interact, they can collide into each other occasionally, but lower entropy state. And what we're really interested in this lecture series are those molecules that are packed closely together, a bit like being in a nightclub where you can't actually move too well, that you're vibrating around in your roughly average same spot, basically held within a crystal. That is not in a club, that would be silly, but in your solid. Okay, so let's think about different properties of solids and their bonding types. So start off with, we have our molecular solids or molecular structures. So this might be iodine or water or carbon dioxide. They're typically good insulators. They have low melting points because they have very weak intermolecular bonds. These can be gases, liquids or solids, and we can actually sublime between the two. Some may dissolve in water, but not many, and many will dissolve in organic solvents, things like hexane. Okay, so our covalent network structures. This is carbon. Okay, so this is our diamond, this is our graphite. We saw graphite in the lab. We've got silicon dioxide, our quartz. We've got boron nitride. These are typically insulators. Although quartz and tourmaline have a really interesting piezoelectric property that if you squeeze them, they will actually generate a current. And this is actually used in quartz watches and such like, but that's just an aside. They have very high melting point because those strong covalent bonds, they're hard and brittle, and they're typically insoluble. Next down, we've got metals. So iron, copper, gold, for example. We know they're fantastic conductors, solids or liquids. Their melting points are typically high. They're malleable and ductile, meaning that you can hammer them into whatever shapes you want, into panels for your cars, etc. Or if you have a prang, you can bend it back out again. Or you can also draw it into wires. So it's very, very malleable and ductile, basically. They're insoluble in water and insoluble in organic solvents. And finally, at the bottom, we have our ionic compounds. So sodium chloride, our table salt, also an evaporite, by the way, magnesium chloride, calcium fluoride. These are examples of ionic compounds. They have a high melting boiling point because they're held together by these very strong Coulombic or ionic bonds. They can be a conductor when in molten or as an electrolyte in solution. They tend to be hard and brittle. Think about your table salt, and they would dissolve in water. Again, think about your table salt, but they won't dissolve in organic solvents. Okay, so moving on, we're going to start by looking at iodine as a molecular structure or molecular solid. Okay, so iodine, as we know, it's a diatomic molecule. It's covalently bonded. Here we have with nice covalent bonds, strong bonds to achieve basically its inert gas configuration. Although those covalent bonds between iodine atoms are strong, these intermolecular forces between them are very weak. So we've just got dispersion forces. And it's a very non-polar molecule. This means that if you warm iodine up, as we've got here, it will actually readily sublime from its solid to gas state. Because iodine is non-polar and its only intermolecular forces are dispersion forces, it's very nearly insoluble. However, it will dissolve in organic solvents such as hexane, because all that's needed is to overcome those weak dispersion forces. Which is kind of handy because you may have come across this thing, this Vetaseptic, or on the right hand side. an antiseptic solution. So povidone iodine is a really, really potent antibacterial. If you've ever had surgery, it's used to sterilize the surgery site. Its carrier is polyvinyl peroxide as a nice stable complex. The cool thing that iodine does is it dissociates from the complex. And then it basically penetrates the microbial cell membranes, and it's that gives its antibacterial property, because then it can interact and mess up those proteins and fatty acids. Okay, so moving on, let's look at our covalent network structures. So good examples here are silicon dioxide quartz, and carbon. They're basically infinite structures held together by really strong covalent bonds, and the structure is found in many non-metal elements. So just one. So we're going to look at basically carbon as our example of our covalent network structure. On the top here is carbon held together by covalent bonds in a tetrahedral arrangement. In other words, each atom is covalently bonded to 4 other atoms, leading to an infinite structure. So you need a lot of thermal energy to actually break those bonds. So this means that our covalent network structures tend to have a very high melting and boiling point. So basically, let's talk a little bit about polymorphs. You'll learn about this with silicon dioxide and quartz, which has a couple of polymorphs, beta cristabalite, which anyhow, I won't digress now. Let's talk about carbon. Okay, let's talk about carbon. So some elements can have the same structure, and can basically some elements can hold the same structure, and carbon is one of them, and this is known as allotropy. Pure carbon can hold one of the can actually be one of the hardest materials known. Remember, it has a Mohs hardness of 10. It also has an absolute hardness of 1600, and if you compare that to tau, which has an absolute hardness of 1, well, it has 1 on both scales. So carbon can actually form 2 different types of covalent network structures. The first is diamond, which we've got at the top here. And as we already said, is held together by strong covalent bonds held in this tetrahedral arrangement, so every carbon is bonded to 4 other carbons. Within diamond, the carbon bonds are formed by sp3 hybrid orbitals, and it's these bonds that makes diamonds so very hard. We also saw graphite on Monday, didn't we? That had a really greasy luster to it. Had a Mohs hardness of 1 to 2. And it has also got covalent network structure. So you've got to think, well, if this covalently bonded the same as diamond, why was it so soft in comparison? Okay, so graphite is actually formed from layers of carbon atoms that are arranged in a trigonal planar environment. So here we have these lovely hexagonal structure. In diamond, the carbon atoms are held together by the sp3 hybrid orbitals, whereas in graphite, those strong covalent bonds occur due to sp2 hybrid orbital interaction. This leaves a pi system, and it's that pi system which is important. So it forms this delocalization over the whole layer as a result of this unhybridized p orbitals, and so this is what forms those very weak interactions between those layers. So when you pick up the graphite, or when you picked it up on Monday and you wrote on the paper, you're actually cleaving the graphite along the sheets, breaking those weak intersheet forces. That's quite incredible. That's just me. Anyhow, we've also got another molecule, which is Buckminster fullerene. It's basically 60 carbons bonded together covalently into discrete buckyballs, as they're known. And between the buckyballs, there are weak intermolecular forces. Basically, buckyballs are therefore soluble. Okay, so this means that it's actually a molecular solid and is not actually a covalent network structure. Even though we've got covalent bonds in there, it's not actually a covalent network structure. And thank goodness, because then I don't have to draw it, which was going to drive me completely bonkers. Then we have a couple of other little kind of quirks of carbon. One of them is graphene. Graphene is a single sheet of graphite. So we've got these graphite sheets which are weakly bonded together. So a single sheet of graphite is graphene. It's transparent. So very different to that what we use the term metallic in a very wrong way as a geologist. So it's in its powdered form, it's still it's still opaque in its finest possible form, but a single sheet of graphite is actually transparent. It was first successfully prepared by Andre Geim and Konstantin Novoselov in 2004 in Manchester, and they actually got a Nobel Peace Prize for it in 2010. Graphene is an excellent electrical conductor, and already ChemCubes is actually out of date because it said that maybe in the future graphene might be able to be used as flexible touchscreen phones. Is already being used for that kind of technology. And then we've got another form of carbon again. So nanotubes, these are cylinders of a single graphite-like sheet. So this covalently bonded graphite sheet with carbon atoms arranged in a hexagonal arrangement. They're about 5 to 15 nanometers in diameter and typically capped with a buckyball type arrangement at either ends. With lengths of several microns, these carbon tubes are thought to have been basically developed with biological applications, including, if you imagine using these as a tiny, tiny little needle delivering drugs to a single cell. Now, I've been going on for far too long now, so I'm going to stop here and allow you to go and grab a drink before I carry on talking about ionic compounds and metals.